Hello and welcome to Circuit Lab. This is practice number 3 of 15, Kitchen Batteries, Series and Parallel Circuits. My name is Mr. Burleson. Last time we talked about the big three, Volta, Ampere, and Ohm, and Ohm's law, V equals IR, which can there be used virtually any time to determine the current and the resistance using the three equations provided here. We also discussed how to identify batteries. Keep in mind, all batteries are going to be direct current. They're usually denoted by their voltage. You've got 1.5 volt, 3 volt, 6 volt, 9 volt, 12 volt, and 24 volt batteries are very standard, but there are other voltages, okay? Now, keep in mind that each one's going to have a positive and a negative terminal, and based on the type of battery, you can usually tell. Like if you'll notice here, the positive terminal always has a little nub right here, whereas the flat side will always be the negative side. And then you'll notice here on a 9 volt battery, okay, the larger terminal here is always going to be the negative, and the smaller terminal is always be positive. Keep in mind that for batteries, they usually break down into two types, dry cell and wet cell. Dry cell has an electrolyte which is immobilized in the paste. So this is what provides the extra holes in electrons to store the charge. A lot of times it'll be zinc carbon. You have a lot of alkaline batteries. Most of your small batteries are going to be dry cell. And what you'll notice over here is you have like a diagram that shows everything from the brass cap all the way down to the zinc can and the carbon rod, okay, which is used to sort of create the different positive and negative terminals. This is one of those examples where I say get a lot of different pictures because you don't know which picture they're going to use. This one happens to be from Wikipedia. There are many, many more out there. And a very common question is to show a diagram and have you say, well, where is the zinc can? Where is the carbon rod? Where would you put the brass cap, etc. Now, a wet cell battery has a liquid electrolyte. Okay, so these are going to be like your lead acid batteries, like car batteries, marine batteries, and as we'll learn later, ones that you can make with soda like Coca-Cola. And then you also have your nickel cadmium and a few other types. You'll notice here on the right hand side you have two different ways of showing a DC independent voltage source. Both are deemed acceptable in that the one on the left usually would show a 2-cell battery, but it's quite often used even when you don't know the number of cells. So a kitchen battery is any type of battery you can make from common materials that you might find in the kitchen. Okay, the reason why is that you'll find that there are a lot of acids available in kitchens that you can use. So what you need to make a good kitchen battery is you need some form of electrolyte, okay, usually something very acidic, okay, which has excess holes and electrons and allows the free movement. And then what you'll do is you'll put in two different metals, okay, and those different metals will then either bring the electrons or bring the holes towards them and form a difference in the potential. So what you'll notice off to the right is that this is a copper on one side, aluminum on the other, and Coca-Cola in a cup. This is very, very common. And you'll notice this particular single cell battery is producing about 0.78 volts. Remember we talked about a multimeter. You'll notice that it's set up to measure voltage, and we're getting 0.783 volts, which is pretty good for a Coke battery, okay? As long as these two metals are different. If you put copper in both sides, this will give you a big old 0. If you put aluminum in both sides, it'll give you a 0. Some other ones that you can use is that you can use seawater, okay? Again, has excess ions available in the solution. You can use lemon juice. You can use just about anything that is acidic. Okay, and so basically any time that you change the type of metals, it'll change. So we'll notice here's another Coke battery where zinc aluminum, which has a bigger difference, okay, gives a bigger voltage of 1.027 volts. Okay. The other thing that you can do is you can actually put these cells in series. You'll always put them in series. But if you put them in series, what you'll find out is that lo and behold, you can add them up. Okay, so what you'll notice here is we have a zinc aluminum seawater battery. Okay, and we put, here's a single cell, and then we hook it into this other one, and we put them in series, and then when we measure them, it's 1.509. So that means that a single cell zinc aluminum seawater battery probably be about 0.75. So you'll notice that the electrolyte also has an impact, as well as the differing metals. So you've probably all heard about potato batteries. And so what you use is that the potato, the juice inside the potato acts as the electrolyte. Okay? And in this case, we use a copper electrode and a zinc electrode. You put them close together, but not touching. And you'll notice it normally produces about 1.2 volts. Now here, you've got a situation where we've got 3 potatoes that we would then put in either, in this case, it looks like they are put in series. Okay, and so if one potato gives you about 1.2 volts, this would give you about 3.6 volts. Okay, and you'll notice it is 3 in series because it's a 3 cell, so each of the potatoes counts as a different cell. Copper, zinc. Okay, so we've got the 2 different metals, and then potatoes are electrolyte. We can also use lemons. Okay, again, here's a copper steel lemon battery. This is another very common one. Okay, so you use a copper electrode and a steel electrode. Put them close together, but not touching. Now you'll notice that a lemon only produces about 0.7 volts. Okay. Now, keep in mind, the steel here could just be provided to you as a paper clip. Okay. And in fact, that's a very common way to do it. Another way is that sometimes if I'm running this event, I'll cut like 6-inch long pieces of copper and 6-inch long pieces of steel, and see if they know how to put them in the lemon and then how to make measurements on them. So now let's talk about equivalent resistance or load. So not all of your circuits are going to be single resistor circuits. In fact, very few of them are. Okay, but it's real easy to solve for a single resistor system. So what we do is we try to simplify the circuit to make it easier to resolve. And one of these ways is to develop what is called the equivalent resistance. In other words, in this particular case, we have a 2-cell battery, and then we have 3 resistors in series. And if we could combine these 3 resistors into a single resistor, okay, and it's the same system, so the system above and below is the same, and R equivalent is equal to however we're going to combine R1, R2, and R3. Now, in a series circuit, the current flowing through both of these circuits is exactly the same. Okay, so what that means is that if this R equivalent is equal to the series addition of R1 plus R2 plus R3, then the current that is flowing out of this positive terminal clockwise is going to be equal to the same current in the below. So a series circuit is like 2 or more resistors in series. Okay, so what this means is that they're in line with each other. The current's going to be the same throughout both of them, because remember, those electrons, like we talked about with the marbles, they got to go somewhere. So if I've got 1 amp coming in here, I have to have 1 amp coming out of here, and 1 amp going into here, and 1 amp coming here, and 1 amp going here, and 1 amp coming here, and 1 amp going back in. That's why you have to have a circuit. Okay? So what happens is that the voltage is split between these resistors. And we'll talk about voltage splitting later, but right now I want you to focus on how do we figure out what's the R equivalent. And a series circuit is really quite simple. Because it's one right after the other and the same current has to go through all of them, R equivalent is equal to all the resistors added up, all the ones that are in series. So in this case, it's R1 plus R2 plus R3 would be our R equivalent. Okay. In this particular case, it would be equal to R1 plus R2 plus R3 plus R4. Remember, there's only one path for the electrons in the holes to flow through. Another thing to always keep in mind is that the R equivalent is always going to be greater than the largest single resistance. So if I've got 1 mega ohm here and 1 ohm and 5 ohms, it's got to be greater than 1 mega ohm. So if I do my math and it's ever less than the largest resistor, I know I made a math error. So let's go through an example. In this particular case, we know that R equivalent is equal to R1 plus R2 plus R3. Okay. And if R1 is equal to 300 ohms and R2 is equal to 300 ohms and R3 is equal to 400 ohms, the R equivalent then becomes 300 plus 400 or 1000 or 1 kilo ohm. Generally speaking, we generally will always make them kilo ohms, mega ohms, giga ohms, whatever it is, so that we don't end up with something like saying 1000 ohms. Okay. Now, if I had a really big battery, like a 1000-volt battery, okay, or 1 kilovolt, I is equal to V divided by R, which would equal to be 1 amp. So as you know, this would be actually really quite a lot of power. So this will be a very powerful circuit here. So keep in mind, R equivalent is going to be equal to the sum of resistors, or if they're the same value, you can just multiply them by that same number. So two 300 ohm resistors in series is 2 times 3 is equal to 600. Three 300 ohm resistors would be 3 times 300, and two 200 resistors in series would be 400. 2 times 200 is 400. The reason why I provide this is that quite often you can look for shortcuts like this once you're really good at combining circuits and simplifying circuits. It's always good to have a few shortcuts on your belt to give you more time. But let's talk about a parallel circuit. So a parallel circuit is where you have a voltage going across, you have the same voltage going across all the resistors. Now you'll notice, so here we have the voltage of the battery and it's going across R1, R2, and R3. Okay, it's the same voltage across each. Now each of these is going to have potentially a different current. And in fact, the current coming out of the battery is actually equal to the current going through all three resistors combined. So definitely the current coming out of the battery is not equal to these. Okay, so the current is split between the resistors. Okay, so in other words, each electron or each hole takes a different path. So the official equation is 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and however many other resistors you have in parallel. R equivalent in this case is always going to be less than the smallest single resistance. Remember, the electrons will always take the path of least resistance. So that means in that case I had before, if this is 1 mega ohm, 1 ohm, and 5 ohms, the R equivalent, whatever I come up with, had better be less than 1 ohm. Okay? And I know for a fact almost, all my current's going to be going through here. I mean, I'll have a little bit going through this one and virtually none going through the big one. Okay? The bigger the resistance, the less the current. Okay? And then the current from the battery is equal to the voltage divided by R equivalent, but keep in mind, each of these has a different current going through. Okay? And if you add up all three of them together, they're equal to the current from the battery. So let's look at this example. It's just a 2 resistor example. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So if R1 and R2 are both equal to 2 ohms, R equivalent ends up being equal to 1 ohm. Okay? Now, if the voltage is equal to 6 volts, okay, then the current coming through the battery is going to be 6 amps. okay, which would then be split among the two resistors. And then if I look at the same situation and I say, well, what's the current going through here? I equal V over R. It's the same V, so it's 6 volts divided by 2. That's 3 amps. And the same equation here, 3 amps. So I'd have 3 amps here, 3 amps here, but I got 6 amps going through this wire and 6 amps going through this wire. So now let's make it 2 4 ohm resistors in parallel. And so the R equivalent ends up being 2 ohms. Again, makes sense. It's less than 4 ohms, which was our smallest resistance. If we put that same V equals 6 volts, okay, we now have 3 amps, okay, which is then split among the two resistors. Well, there's something to always look for here. If the resistors have the same value, the resistance is equal, the R equivalent is equal to the number or the resistance divided by the number in parallel. So 2 4 ohm resistors in parallel will be 4 ohms divided by 2 is equal to 2. 2 6 ohm resistors in parallel is 4 ohms divided by 2 is equal to 3. And 3 6 ohm resistors means 6 ohms divided by 3 is equal to 2 ohms. This is really important because unlike series, it's sometimes difficult to calculate parallel, especially when you get multiple parallel. But to take this to the extreme, if I have 1,000 kilo ohm resistors in parallel, that will give me the same resistance as a single 1 ohm resistor, because it would be 1 kilo ohm divided by 1,000. And so you can imagine trying to do that on paper would be virtually impossible, but through this shortcut I can easily calculate that value. So generally speaking, grab a quiz from your coach, use your binder, and see how you do. Now, for a practical, what I'd really like for your coaches to do is to provide you some simple materials so that you can try to create a kitchen battery. Use some of the ones earlier, you know, either a Coke one, a saltwater one, a lemon one, a potato one, etc. Okay? Measure the voltage and determine which is the positive and which one's the negative. Identify which parts of the electrolyte, which part's the cathode, which part's the anode. And yes, I want you to look those up as well. I'd like you to create a couple of these that are the same and then create a series circuit, okay, so that you can see the different voltage between a single cell and a multi-cell battery. Then what I'd like you to do is also go and create a series circuit where you put a few resistors in series and measure the resistance across the across each individual part and then all the way down. Then I want you to also do the same thing with a parallel circuit and resistance. And again, what you're looking for here is looking how the voltage is split, and you're going to look at how the resistance is equivalent to your calculations. Homework. What I'd like you to do is just describe the difference between wet and dry cell batteries. Give some examples, okay? Give 2 examples of kitchen batteries, including terminal notation. In other words, which one's the positive, which one's the negative, which one's the cathode, and which one's the anode. What type of materials are used for the terminals? What are the electrolytes? If I need to have the same voltage for all elements, would parallel or series circuit be better? If I need to have the same current for all elements, would a parallel or series circuit be better? And I'd like you to do 2 sheets now. I'd like you to do both level 1 VIR and level 2 parallel. So it'll be a little bit of a step up in difficulty. Thank you so much, and